Let's begin our discussion with binary numbers. Now, when you hear the word bi, what do you think of? Bi is associated with the number 2. And so binary numbers have only two possibilities, 0 or 1. Now, when dealing with circuits, 0 is, or it corresponds to a circuit being in the off state. 1 corresponds to a circuit being in the on state. So if you're dealing with true and false statements, an off state will be considered false, and on state would be considered true.
Inside your computer are billions of units called transistors. These transistors serve a variety of purposes, but they commonly act as a sort of very small light switch. Each switch can be turned on or turned off. Computer scientists will often represent a switch that's turned on with the number 1, and a switch that's turned off with the number 0. These zeros and ones form a number system called binary, and it's the fundamental language of computers. From just these zeros and ones, we end up with computers that can perform calculations, create documents, view images, browse the web, and more. How does that happen? In this series, we'll explore the foundations of computer logic, starting from the fundamentals. Using these switches, our computers can store information. More and more sophisticated. Each switch stores a single bit of information, a 0 or a 1. But computers don't just store information, they process it, transforming inputs into outputs. That's where logic gates come in. Logic gates are the building blocks of computer circuits. They accept input and produce output according to a set of logical rules. One of the simplest logic gates is the NOT gate, represented graphically here. The NOT gate takes a single input, either a 0 or a 1, and inverts it, so that the output is the opposite of whatever the input is. If the input is a 1, then the NOT gate outputs a 0. If the input is a 0, then the NOT gate outputs a 1. To represent the logical rule this gate obeys, we can draw a truth table, which is just a way of writing down the rules for some logical formula. This table says that if the input is 0, then the output is 1, and if the input is 1, the output is 0. Often, though, our computers need to be able to perform calculations not just on a single bit of information, but on multiple bits of information. The AND gate, shown here for example, is a logic gate that takes 2 inputs instead of 1. Let's call these 2 inputs A and B. As the name might suggest, the AND gate will output a 1 when both A and B are 1s, but in all other cases, AND will output a 0. We can construct a truth table here too. This truth table is a bit bigger, since with 2 inputs there are more possibilities to consider. If A and B are 0, the output is 0. If A is 0 and B is 1, the output is 0. If A is 1 and B is 0, the output is still 0, and only when both A and B are 1s is the output a 1. The OR gate, meanwhile, is also a logic gate that takes 2 inputs. This gate outputs a 1 when A is a 1, or when B is a 1. So if both inputs are 0, the OR gate outputs a 0. But if either of the inputs is a 1, or both inputs are a 1, then the output of the OR gate is also going to be a 1. These logic gates on their own follow fairly simple rules, but they can combine with each other to form more complex calculations. Imagine what would happen if, for example, we took 2 inputs, passed them into an AND gate, and then passed that output into a NOT gate. What would happen? If both inputs are 0, the AND gate will output a 0, and the NOT will turn that 0 into a 1. If only one of the inputs is a 0, nothing changes. But if both inputs are 1, the AND gate will output a 1, and the NOT will turn that 1 into a 0. In other words, this circuit appears to do the opposite of whatever the AND gate on its own would do.